Now in our class, we did the full breakdown of all three N modes of motion for a water molecule. And you saw that by adding X, Y, and Z axes to every atom on the molecule, you could determine all modes of motion for a molecule. Now doing so for more complicated or larger molecules would be incredibly tedious. In fact, even for me, it would take hours and hours to do for a molecule like this. Importantly, though, oftentimes what chemists are interested in are just specific parts of the molecule, and in certain cases, just specific stretching frequencies or bending frequencies when using this approach to determining the number of IR frequencies or the number of Raman frequencies. And this can be really useful for chemists in structure determination. And what you see in front of you is a molecule that I'm going to walk through showing you how I can just find just the CO stretching frequencies. Now, this carbon monoxide in here, don't forget, is a triple bond, which means that it can't bend because of that alkyne, that triple bond that's present right there. Which means that the only type of frequency that we would expect to see on IR or Raman spectroscopy would be the stretching of this molecule. Okay, so in fact, what I could do is just look for the overall stretching modes for the CO bond in particular by using a very similar approach. By generating a reducible representation denoted by the capital gamma symbol, not for all three N modes of motion, but just specifically for CO stretching frequencies. Okay, and we can do that by treating each of these bonds as a vector. So if I were to treat this as just a simple vector, then what I could do is place vectors on each of these CO bonds and solve for the reducible representation gamma just for the changes that are occurring in the CO stretching frequencies. Okay, so we've identified that there are 4 CO bonds, and potentially we could come up with the series of all CO stretching frequencies. And in order to do that, the first step that we need to do is determine the point group, which is why it was so important to review that material previously. So if I'm looking at this molecule, to me what instantly jumps out is that going between the Br to the manganese to the CO, straight up and down in the axial position, that is likely to be my principal rotation axis. And I see that I can do a C4 rotation by rotating 90 degrees. The Br and the CO at the top and the bottom would remain in the same place, and these COs would switch into positions that would make the molecule look identical. So I'm going to say that this axis right here is likely to be my principal rotation axis, and it's a C4 axis. The next step in determining point groups would be to see if there are any perpendicular to the principal axis C2 rotations. So perpendicular would be going in and out of the screen through manganese, and I see that if I did a C2 rotation or a 180 degree rotation, all 4 of these COs would be in the same position. However, this CO and this Br would switch spots. So that one's not possible. The other perpendicular axis is going to be this one. And I look at this and I say, okay, if I did a 180 degree flip of this molecule, again, all 4 of these COs would remain in position. However, again, the CO and the Br would switch. Therefore, there is no C2 perpendicular rotation axis. This tells me immediately that this is going to be a C point group, specifically a C4 something. Whether or not it's C4H or C4D or C4B, we still need to determine that. So the next step then I need to see if there are any sigma V or mirror planes that go through bonds in this molecule. And for that symmetry operation, I can see that the plane that runs through each of these CO bonds is a mirror plane. And what would be reflected would be this CO stretch into this CO, and everything else would remain in its position, and the molecule would still look the same. In fact, there's another one that bisects the other COs, wherein these would flip and everything else would remain the same. Therefore, this molecule does have a sigma V, and using the flowchart, I would know then that this must be the C4V point group. There are sigma Ds present in here, so if you remember, the sigma D is a mirror plane reflected through the dihedral angle, so the angle between this CO, manganese, and CO. There is a sigma D, however, we haven't gotten to that on our flowchart, and that allows us to assign sigma 4b. Alright, so if you were then to go and look up a character table for C4b, you would see that it is made up of the identity operation, always, the fact that there are two C4 rotations, there are one C2 rotation, there are two sigma b's, and two sigma d's. Now, I don't just have that memorized, and I don't expect you to have it memorized. I obviously looked up the character table before beginning this question. So, now as we begin to generate our reducible representation for specifically the CO stretches, I need to refer back to what is happening to these vectors that I've put in as I perform these symmetry operations. So, if I were to do identity, again, that obviously means that everything just stays exactly where it is. Therefore, I would notice that there are 1, 2, 3, 4, 5 of these vectors that do not move whatsoever. Therefore, because neither of those 5 vectors move, I'm going to place a 5. So a 1 for every instance that the CO doesn't move. The next thing would be if you performed a C4. If you performed a C4, sure, it's true that all of the COs the molecule would look identical. However, here we're not concerned with whether or not the molecule looks identical. We're concerned with whether or not these vectors have moved into new locations. So even though they look identical, this vector is not the same as this vector. Therefore, they are moving, so all 4 of these vectors move, so they get 0 as the character. The only one that remains the same is through this principal rotation axis in this bottom CO vector. That means I should have a character of 1. The next thing is the C2 rotation, which again is going up and down through the molecule. And if I were to do a 180-degree turn, what I would see is that each of these vectors would be moving, and the only one that would remain in the same position would be this downward CO stretch. So I'm going to place a 1 here. The next thing that I need to do is look at my reflections through the mirror plane that actually contain the bond axis, or the sigma b, the vertical through the principal rotation axis. Alright, so if I were to choose this one that I've already drawn on the board, it contains this CO stretch, it contains this CO stretch, and it contains this CO stretch. What is being reflected, again, is this vector into this vector, and this vector into this vector. Therefore, these two flip, so they are no longer in the same location, so those get zeros. 3, however, are remaining in the same position, so I'm going to place a 3 underneath the sigma b symmetry operation. The next one is going to be our sigma d, or the dihedral, which again bisects the molecule, so right in between each of these CO stretches, again, that is the dihedral angle. And as we see, if we were to place a mirror in between this molecule, then each of these COs would flip, therefore they would be moving, and the only one that would remain in the same position is going to be this bottom CO stretch. So I'm going to place a 1 underneath the sigma d symmetry operation. And this gives me my reducible representation for just the CO stretches, only concerning ourselves with the CO stretches, not all 3 end modes of motion for the entire molecule. And now we can begin to reduce this reducible representation. Now that we've generated our reducible representation for the CO stretches, we need the character table for C4b. And this you will always be provided. I'm never going to ask you to memorize it or to create it independently. I will always provide for you the character tables that you need. Or on homework, for example, you can just look them up. So, now that we have our reducible representation, we need to reduce it to see which of these irreducible representations, denoted by these Millikan symbols, make up our reducible representation. And that's what the reducible representation tells us. It's which of these irreducible representations are actually contributing to this overall reducible representation. And it should be a sum that adds up to this reducible representation. And we do that using the reduction formula. So we're going to walk through a couple of these, starting with A1. So for A1, what I'm trying to do is figure out how many A1s actually are present in this reducible representation. And you begin by taking 1 over the order, which is the number of symmetry operations present in a C4V molecule. So there's an invisible 1 here, plus 2 is 3, plus 1 more is going to give us 4, plus 2 is 6, plus 2 is a total of 8. So the order of a C4V molecule is 8, and it's always 1 over 8. And then you take the sum of all the other things that we're about to do. So we're going to break that down. We start by multiplying the coefficient in front of the symmetry operation. So 1 times 5 times the character that's present that corresponds to that symmetry operation in the character table. So 1 times 5 times 1. So 1 times 1 times 5 plus, then we just move on to the next symmetry operation. 2 times 1 times 1. So 2 times 1 times 1. Plus 1 times 1 times 1 for C2, 1 times 1 times 1, plus 2 times 3 times 1 for the sigma V, so 2 times 3 times 1, plus 2 times 1 times 1 for the sigma D, so 2 times 1 times 1. All right, now let's work out this math. So 1 over 8, we got 5 plus 2 plus 1, plus 6, plus 2. This looks like 7, plus 1 is 8, plus another 8 is 16. Divided by 8 is equal to 2. Now this tells me the number of A1s that are present in my reducible representation. So I know that for sure there are going to be 2 A1s. And we can walk through and do that for all of these, which is what we have to do to figure out how many of these irreducible representations make up our reducible representation. So now if we go through, and I'm just going to skip around and you'll work these independently, and I'm going to jump to B1, for example. So I'm trying to figure out now how many B1s are present. So the number of B1s, again, 1 over the order, which is 8. 1 times 5 times 1, which is 5. Plus 2 times 1 times negative 1. So now we got a negative 2. So I'm going to put a negative 2 there. Don't forget that this is a negative. And then we'll jump over to C2 where it's 1 times 1 times 1. So that's going to be 1. Plus 2 times 3 times 1, which is going to be 6. Plus 2 times 1 times negative 1. So that's a negative 2. All right, so now if we work out this math, we got 5 minus 2 is 3, plus 1 is 4, plus 6 is 10, minus 2 is 8, and 1 over 8 is equal to 1. So I know that there is one B1 present in this reducible representation. Now let's jump around some more and figure out how many E's there are. Don't forget that this E in the character table is different than this E, which tells you the symmetry operation. This E tells you that it's doubly degenerate, or that things happen with the exact same energy. And we actually know that because the functions that are present in the character table that correspond to the linear and the quadratic functions are contained in parentheses, meaning that they move at the same time with the same energy. So now that we're looking at E, we are again doing 1 over the order, which is 8. And then we're going to take 1 times 5 times 2, which is 10, plus 2 times 1 times 0. Well, that's convenient. 0. And then we have 1 times 1 times negative 2, which is going to be a negative 2, plus 2 times 3 times 0, and the other one is also 0, so those are both zeros. So then here I see that we have 10 minus 2 is 8. 1 divided by 8 times 8 is equal to 1. So therefore, I know that present in my reducible representation for the CO stretches, there is one E, which means that I can rewrite my reducible representation. Instead of being this, I can rewrite it as my reducible representation for the CO stretches is equal to 2 A1s plus 1 B1 plus 1 E. And in fact, the reason that I skipped A2 and B2 is because they actually equal 0. So they're not actually present in our reducible representation. Now, I knew that because I'd worked out this problem independently, but you will have to work out each of these and see which of them are present in your reducible representation. So this makes up our reducible representation for the CO stretches in this molecule. Now, what can we do with this information now that we have determined the overall number of the reducible representation and the irreducible representations that make that up? Now I can say to myself, okay, how many IR active modes should I see if I took an IR of this molecule for CO stretches? Well, I need to come over for IR active modes. I'm looking in our linear functions. So this first column following all these values in the character table. And it turns out that IR moves when you have a dipole shift in the X, Y, and Z. So I'm looking in this column for X, Y, and Z. And I see that for an A1, it is IR active. And I also see that for E, which is doubly degenerate, there is an X and a Y, which is telling me that there are also going to be IR active modes there. Notice, however, for B1, that there is nothing in this column, so in fact, that is not going to have an IR active mode. For Raman active modes, I'm looking for a change in the polarizability of the molecule, and those track with the quadratic functions that correspond to the d orbitals. So notice that under A1, you see a z squared. That corresponds to the dz squared orbital, and since the A1 is present in our reducible representation, I know that it's going to have Raman active modes and IR active modes. For B1, we said that there were no IR active modes, but there is an x squared minus y squared in the quadratic function, and this tells us that there is going to be a Raman active mode for the B1. And then again for the E value, or E reducible representation, apologies that over here in the tiny corner, but there's an XZ and a YZ. That tells us that they're going to have Raman active modes because there is a value in that column as well. And this is what we're trying to do with these molecules. So now I'm going to put on the screen one for you to try. Alright, hopefully you were able to determine that this is a C2V molecule where the C2 axis is going through this CO, the metal center, and the Cl. If you rotate 180 degrees, everything flips and looks the exact same. You also have a sigma V in the x direction, meaning that it contains basically this plane of molecules here. Thus, the only thing that gets reflected through the mirror plane are these two chlorides. And then you also have another sigma V that contains the principal axis, in which everything, these two flip, where the mirror plane would contain all four of these molecules. So, now that we know that it is C2V, we need to figure out what is going to be our reducible representation for just the CO stretches. Okay, so we're trying to figure out the CO stretches, and we see in the character table that we have an E, we have a C2 principal rotation axis, we have a sigma V in the XZ direction, and we also have another sigma V in the YZ direction. All right, so now that we know that, we can determine our reducible representation. So we need to turn all of these CO stretches into vectors so that we can track them as we perform these symmetry operations and see whether or not they move or stay in the same place. So for identity, all three of them stay in the exact same place. Nothing moves for identity, so we'll put a character of 3 underneath the E. For the C2, again, it contains this axis right here where you have the CO going through to the Cl, and that principal rotation axis is C2. And we notice that when we do a 180 degree turn, that these two move, but the only one that stays the same is the one that is contained within the principal rotation axis. So that's going to give us a character of 1 because the two moving get zeros. The sigma V in the XZ direction is going to be the plane of these 4 ligands, where the only thing that are not contained in that mirror plane is going to be the 2 chlorides on top. And this lets us know, since the mirror plane contains all 3 of these vectors, that all 3 of them stay in the exact same place. And then for the sigma V in the YZ direction, it is cutting through these 4 ligands, and that means that these 2 vectors get flipped upon reflection through the mirror plane, so they get zeros, and this one is the only one that stays the same, so it gets a 1. So our reducible representation for the CO stretches of this molecule is going to be 3, 1, 3, 1. Now we need to begin to reduce it to figure out which of these irreducible representations make up our overall reducible representation. So the order for this one is going to be 1 plus 1 plus 1 plus 1, all invisible 1 stoichiometric coefficients there, so that's 4. And then we'll take 1 times 3 times 1, for A1 is going to be a 3, plus 1 times 1 times 1 is going to be a 1, times 1 times 3 times 1 is going to be a 3, times 1 times 1 times 1, which is going to be a 1, and that gives us 4 plus 4 is 8, divided by 4 is 2. So there are 2 A1s present in this reducible representation. Now if we quickly go through the rest, for A2, again we start with 1 over the order, which is 4. We see 1 times 3 times 1, which is 3, plus 1 times 1 times 1, which is 1, plus 1 times 3 times negative 1, that's going to be a negative 3, times 1 times 1, plus 1 times 1 times negative 1. So these end up being 0, and then that tells us that there are no A2s present in our reducible representation. Now if we go to figuring out for B1 how many there are, we have a 1 over 4. We got 1 times 3 times 1, which is 3, plus 1 times negative 1, plus 1 times 3 times 1, which is 3, plus 1 times negative 1, which is going to be a negative 1. So this means that we end up with 3 minus 1 is 2, plus 3 minus 1 is 2. That gives us 2 plus 2, which is 4. 1 over 4 is equal to 1. Then for determining how many B2s are present in our reducible representation, again it's 1 over 4, which is the order of the symmetry operations. We have a 1 times 3 times 1, which is 3, plus 1 times negative 1, plus 1 times 3 times negative 1, which is a negative 3, plus 1 times 1 times 1. 1 times 1 times 1. So this also 3 minus 3 is 0, negative 1 plus 1 is 0, so this is 0. I often get asked questions, what do you do if you don't get a whole number here? That actually means that you did it wrong. You'll always get a whole number. You shouldn't have any fractions whatsoever. So now that we have done our reduction formula to figure out how many make up this CO stretch, we know that now we can clearly see that there are 2 A1s and 1 B1 that make up our irreducible representations that make up our reducible representation for the CO stretches. Now we need to determine how many IR peaks to expect for this molecule for the CO stretches. We go to A1 and we go to the linear function and we see if there's an X, Y, or Z there. And it turns out that there is a Z, which tells us that there's going to be 2 peaks for these. And then we go to the B1 and we go and see that there is an X there. So we need an X, Y, or Z to be contained in that column for the B1 irreducible representation. So that means that all of these should be IR active, which means I should have 3 IR peaks for stretches. There's 2 from the A1 because we're multiplying 2 A1s. There is 1 for the B1 because there's only 1 here, so there's 3 overall. Now we need to determine how many IR active peaks there are. Again, we're using the same irreducible representations. We go to A1 and we see that there is an X squared minus Y squared and a Z squared, which means that we're going to have 2 for that. Plus our B1, we see that there's an XZ in the quadratic function. So that tells us that there is going to be 3 Raman peaks. So therefore, we should expect to see 3 IR peaks and 3 Raman peaks for the CO stretches here. And this is going to be really helpful in structure determination, which is why chemists are so interested in using group theory to break down exactly how many vibrational modes there are for molecules.